Alright, so let's talk about sequences. What did you learn about sequences in your calculus class? Well, you might have heard that sequence is a set of numbers. But now you are in real analysis class. So in real analysis class, you have to give a formal definition for a sequence. So let's do that by using an example. So let's construct an example. Let's take a famous sequence. 1, 1/2, 1/3, 1/4, 1/5, and so on. Now this is an infinite sequence. Why it's an infinite sequence? Because you can write this forever. Let's say like that. Okay. All right. Now what I'm gonna do is, well, in this sequence I can say this is the first position, this is the second position, and this one is the third position, this one is the fourth position. So for each position I can pinpoint a term in the sequence, right? So tell me, what is the 1000th term of this sequence? 1000 is the position. What is the 1000th term? 1/1000. What is the 10,000th term? 1/10,000, right? Okay, perfect. Now let's rewrite this sequence in a different manner, like this. So let me draw two circles. In the first circle, let's put the position. First position, second position, third position, fourth position, and you can do this forever, right? Okay, so 1, 1/2. Oh, in the second circle, I'm gonna put the terms of the sequence. Now let's see the relation. First position is 1, second position is half, third position is 1/3, fourth position is 1/4, fifth position is 1/5. Now when you see this picture, what comes to your mind? Think about this carefully. It's a map, right? Question is, from where to where? In the first circle, what type of numbers you have? We know we have real numbers, complex numbers, rational numbers, natural numbers, integers. What type of numbers you have in this first circle? Natural numbers, right? The numbers that you can count. All right. Then on the second circle, what type of numbers you can have? The hint is, what is the name of the class that you are in right now? Real analysis. So you should have real numbers. So this is a map from natural number system to real number system. Now this map is injective. What is injective means? For each position in the first circle, you have a one term in the sequence, and that makes sense, right? When I say the 1000th position, the term is 1/1000. For each position you have just a one term, right? Now when I say 1000th position, can you say like, oh, is it 1/1000? It is 1/1005? No, you don't have hesitation, right? For 1000th position, it's 1/1000, one-to-one relationship, so we call it injective. Now is it surjective? That means for each term, at least can you find a one position? Of course, yes, right? Let's say the term is, take a random term, 1/3000. That's a term in the sequence, right? It has to be in the sequence, right? So can you find its position? Of course, yes. You can say it's 30,000. 30,000th position. You can find a one, right? So it is surjective. So this map is bijective. And that brings us to a conclusion that sequence is a function. Yes, sequence is a function. So that's the transition we take from calculus class to our real analysis class, from set of numbers to a function. Okay, so we can write it in different ways. In different books, several teachers use different type of notation. So let's address that. Well, we can define this map from n to r, and we can say if n given n. Now see, simple n is the domain. The natural number set is the domain of this function, right? We can write this particular function represent as 1/n. Given the nth position, 1/n will give you the term. And the domain is, of course, the natural number system. Okay, now there's another way to represent this. Like a sub n, simple n is again the position, we can say 1/n, and we can say here it belongs to not the integers, natural number system. Okay, There's another way. There's another famous notation people use from in 1 to infinity. That means the positions are running from 1 to infinity. That's another way to say the natural number system. And you can also start from 0. Don't get me wrong, okay? You can say the 0th position, 1st position. You can do it in that way also, okay? So this is just, we are representing the limits of the position. Well, it's not the limit that we learn in calculus classes. No, limit is a bad word to use there, so forget about that one. But that's from where to where is it running from? 1 to infinity. All right, so let me show you another different example. So let's question ourselves. Is sequence always a function? Let's represent this sequence, -1 to n, and n also belong to natural number system. So let's write the terms of this sequence: -1, 1, -1, -1. Right? You can, when n is equal to 1, -1 to the 1 is -1, so and so on. We can write the terms of this sequence. Let's put them in a 2 circles. Position 1, 2, 3, 4, 5. So this is natural number system, the domain. And here we only have just 2 terms, -1 and 1, right? So let's map. First position is -1. Second position is 1. Oh, third position is -1. Fourth position is 1. Now, so fifth position is again -1. So it seems to be like it's not a one-to-one map, right? No, it's not a one-to-one map. So then it brings us a question: is this a function? Yes, it is still a function, because you can have one-to-one, but what you should not have if it is not to become a function. You cannot have a one-to-many relation, right? So what is a one-to-many relationship mean? So for example, in terms of sequences, for each position, for let's say for the second position, can you have 2 terms? That's not possible. Is that what happening here? Well, for the first position you have -1, just a -1. Okay, for second position you have 1, just a 1. So it's not a one-to-many relationship, it's a many-to-one relationship, right? So 1 also have -1, 3 also have -1, fifth position also -1. So first position, third position, fifth position, seventh position, they all go to -1. So this is a many-one relationship. That's the difference. It is not a one-many relation. So that means you can have when you have a many-one relation, that's still a function. So this is still a function. Okay, all right. Now, well, we can represent this function again from going from in this sequence from 1 to infinity. All right, now that's another example. So let's look at another way you can write a sequence, a very important one. We can write a sequence in a recursive way. What do I mean? So look at this sequence. A sub n plus 1 is a sub n plus 2. Now here, this is another way to represent the sequence. I can represent the sequence using from the previous terms of the sequence, okay? But to do this, in here, for example, you have to give at least what is my first term. So let's say my first term of the sequence should be 1. Now if the first term is 1, what is the second term? Well, second term is first term plus 2, which is 1 plus 2, which is 3. What is the third term? 3 plus 2, 5. So we can write the sequence as 1, 3, 5. It will give 7, 9, so and so on. Okay, so this is another way you can write a sequence in a recursive way. Let's look at another famous sequence that is defined like that. A Fibonacci sequence. Look at the Fibonacci sequence. Fibonacci sequence, we use A. So A n plus 1 is a n minus 1 plus a n. Now here this is defined for n greater than or equal to 2. We have to have, so in this sequence, for example, if you want to write the terms, we have to know the first term and the second term. So let's say the first term is 1, the second term is 1. Now then the third term, that means that means here a2 plus a1, okay, which is 1 plus 1, third term is 2. Now let's find the fourth term, which will be 2 plus, well, a3 plus a2, okay, so that is 2 plus 1, which is 3. So the sequence is 1 1 2 3, okay, and next one will be 5, so and so on. You can build up the sequence. So this is the Fibonacci sequence, okay, but it's still a function, all right, and that's what we learn in this video. The biggest takeaway is that the sequence is a function, all right. That's the transition that we took from calculus class to real analysis class. Now in the next video we are going to learn the definition for convergence of a sequence. We are going to learn that in a different way than what you have learned in your calculus class. So make sure you watch the next video. So hoping that you are watching the next video. I will say bye to you right now. Okay, so then I'll see you in the next video. Thank you for watching this video. Bye bye.